Okay. Well, it's my pleasure to introduce our seminar speaker, Dr. Chaspari. She is actually from the Department of Computer Science Engineering here at Texas A&M. Her research interests focus on integrated computational study of physical well-being and human behavior through the use of both overt behavioral signal information, for example, speech and language, and covert biomarkers, for example, biomedical signals, as well as systems theoretical modeling of human interactions. She has been working on integrating the data scientific and context-rich biobehavioral approaches towards novel individualized diagnostics, rehabilitations, and intervention tools, including human-assisted biofeedback systems for empowering well-being, health, and defense applications. So if I can ask you to share your screen and the slides. Okay, yeah, I can see your slides now. Yeah, so she's going to talk about, tell us about her recent work on designing personalized and privacy-aware machine learning for promoting well-being, health, and education. Dr. Chaspari, please take it away.
Thank you so much. Thank you very much, Yang, and thank you everyone for the great invitation. It's very nice to be here in the statistics department today, and I'm very excited to hear all the conversations with everybody. So the title, so today's talk, we're going to discuss about ways to model and quantify human behavior and how we can use data scientific and machine learning solutions inspired by problems in psychology and health sciences in general, in order to solve and better model and quantify human behavior. So human behavior is a multifaceted phenomenon that involves the interaction of the mind, the body, and the brain, and we can get access to human behavior by leveraging various sources of information. In our case, we are trying to leverage what we call overt behavioral cues, which correspond to speech signals, facial expressions, body and body gestures. Behavioral cues like that indicate communicative intent and can also indicate several types of mental or cognitive disorders that people might have. On the other side, we're also trying to take into account generative processes that are happening inside the human body, through which we can get access using physiological signals and physiological monitoring equipment. Such signals include heart activity, brain activity, sweat activity, or even respiration. Finally, another important factor that affects human behavior is the interacting environment around us. So as humans, we are not really isolated. We are interacting with people around us. We are interacting with our co-workers, with our spouses, with our friends, and we are also interacting with the environment around us. And all this can really play a significant role in shaping multiple facets of human behavior. So what we're trying to do in the Human Biobehavioral Signals Laboratory is that we are providing an integrated computational study of human behavior, physical well-being, and mental health. We are taking into advantage overt and covert signal biomarkers, and we're trying to design novel data scientific and context-rich mathematical and machine learning models in order to model behavioral outcomes that are mostly focused on cognitive outcomes, emotional outcomes, and mental outcomes. So in that endeavor, we are attempting to provide new algorithmic and engineering solutions, as well as novel work with our psychology partners to provide novel individualized diagnostic and therapeutic tools. And of course, a very important part of our work is that we are also trying to get inspired, but also inform life sciences in order to promote scientific discovery overall. A big support in what we're doing is the advent of wearable technology, which now allows us to collect human behavior really from outside the lab in unconstrained conditions, and also get more naturalistic expressions of human behavior. And also the advent of Internet of Things devices that allow us to contextualize the information that we get from our wearable sensors. So for example, GPS coordinates that there are on our phone allow us to contextualize that the person, let's say, is at the park running at a specific point of the day, so their heart rate increases because they are running and not because they are performing a mental task. So in that endeavor, we are trying to address various challenges that come with this. First and foremost, there is a very high inter-individual variability in the data and in the way people express their feelings, their emotions, and their cognitive load. For example, the way one person expresses their happiness or their anger might be completely different from the way another expression does that. And that can depend on demographic characteristics, psychological traits, as well as cognitive characteristics. We are trying to integrate confounding factors that we get from the environment and provide robust and behavioral meaningful representations from the signal that we are modeling. And finally, we are also attempting to mitigate privacy considerations, especially in relation to user re-identification. And as part of our later work, we have been trying to design anonymized machine learning models that do not preserve user-dependent information. So as part of this work, we're going to present today 3 research threads that we have been working on. The first research thread focuses on personalized biobehavioral training, which essentially attempts to capture various sources of signals that come from speech, physiology, in order to understand when a person feels more stressed or feels more anxious about their training. And then our goal is to provide in-the-moment feedback and interventions that can increase the training effectiveness based on this person's biobehavioral expression. The second thread that we are going to see relates on real-life tracking of human behavior. So we're going to see several case studies in which we have used wearable devices and IoT devices in order to track behavioral outcomes. And finally, the third thread would be focused on anonymized behavior-aware machine learning. So now going a little bit more into the first thread on personalized biobehavioral training, we provide a test bed in which we have attempted as part of one project to to develop a new personalized public speaking anxiety training. So the motivation behind this is that we know that many people suffer from public speaking anxiety, which leads to high levels of physiological activity, various negative thoughts, as well as tangible behavioral reactions such as trembling. So the overall goal of this project is to design adaptive training interfaces that can estimate a user's anxiety in real time and provide individualized feedback. Our goal there is not to provide this feedback while a person is actually performing the task, but just to provide this feedback during training so that we can try to attempt to have some cognitive restructuring of the negative thoughts that might be occurring during that time. So for example, if we see that the person might be getting stressed, we might tell them, you know, you're doing great, don't worry, the audience is not judging you. And in this way, during training, hopefully we're going to be able to provide some restructuring of the negative thoughts that occurs in that person. So what we envision this to be is to be at the intersection of studies that have happened in psychology and communication sciences, affective computing, as well as personalized behavioral interventions. And as part of the work that we have been doing in that front in the last 2 years, we attempted to answer 3 overarching research questions. The first question was whether we can quantify public speaking anxiety from wearable-based data that we get. The second question was how to develop group-specific models of public speaking anxiety in order to take into account the inherently high inter-individual differences. And then the third research question was whether systematic exposure to public speaking anxiety can alleviate systematic exposure to public speaking can actually alleviate public speaking anxiety. And in that front, we developed a data collection paradigm in which we had participants that came in the lab in 3 research parts. During the first research part that we call the pre, participants had to give a public speaking presentation in front of a real-life audience. And on this public speaking presentation, participants first had to prepare an article from the media for 10 minutes. And then based on their preparation, they came into another room where an audience was, a small size audience was waiting for them, and then they gave the public speaking presentation. In this pre-session, we had 55 participants. Then part of these participants did what we call testing. So during testing, basically that was our training, our VR training, in which participants were provided 8 VR sessions based on which they had to present in front of different types of virtual audiences, which varied in terms of size, difficulty, and reactions. And finally, the participants came back to the lab to perform again a real-life presentation, so that this real-life presentation could be compared with the real-life presentation in which participants did before the VR training. These are examples of several types of audiences that we managed to have participants work with. You can see various room settings, various audience sizes, as well as various percentage of demographic characteristics in the audience. And we also integrated some background noise in order to make the conditions more realistic. We used various wearable devices in order to collect our data. Specifically, we collected data from sweat activity, which is what we call the electrodermal activity signal. We also used heart rate and electrocardiogram in order to get measures of heart activity. And we also used a lapel microphone in order to get speech measures, specifically speech intonation, that might be actually, previous studies have indicated that this is very much associated with anxiety and stress. And overall, we had 82 real-life presentations and 216 virtual reality presentations. So these are some examples of how our data looks like. On the left part of the screen, you can see the first part here is our electrodermal activity signal. And you can see that the electrodermal activity signal stays pretty low during the relaxation period and the preparation period, but then it increases during the presentation. And here you can see how, on the right part of the screen, you can see how our EDA signal varies along the 4 virtual reality sessions. And these are some very interesting trends. In every VR session, we have a peak in the electrodermal activity signal. Based on the signals that we collected, we extracted various measures. For example, from the electrodermal activity, we extracted the mean, the amplitude, and the frequency characteristics of the signal. In terms of heart rate, we extracted heart rate variability, interbeat interval, and various time and frequency-based measures. And in terms of acoustic features, we were also able to extract the speech loudness, the fundamental frequency, the number of pauses, as well as the jitter and shimmer, which are measures that are related to the trembling of the voice, which is something that might be especially relevant for the public speaking task. So we further collected various demographic factors and psychological traits, such as age, gender, ethnicity, education, the Big 5 inventory in order to collect personality characteristics, as well as trait anxiety characteristics. And in order to assess the public speaking anxiety in real time, we had participants retrospectively indicate their perceived levels of anxiety during the task. So we used for that several types of validated research questionnaires, and we are now in the process in which we are having third-party annotators actually rate the participants in terms of this perceived anxiety. So in terms of answering our first research question on whether we can quantify public speaking anxiety from wearable-based biobehavioral measures, we attempted to train simple linear regression models. The input of the linear regression models was the various measures from the various modalities that we got from our wearable sensors, and then the output was the estimate public speaking anxiety metrics that we got from the self-reports. And we see various correlation levels here. that vary between 0.18 when we have this CWP, which are the chest-worn physiological measures, as well as a combination, let's say, of chest-worn measures and wrist-worn measures, yielding a correlation of 0.3. And similar correlations we have with when combining the acoustic measures and chest-worn measures. So this indicates some type of feasibility in that we can at least detect facets of public speaking anxiety from our biobehavioral signals. Then we went to the second research question, in which we wanted to examine inter-individual differences. In our data, we observed various differences in perceived public speaking anxiety in terms of education level. So, for example, undergraduate students perceived this task a little bit more stressful compared to graduate students, and the same difference was also reflected in their sweat signals. And we also observed some differences in terms of ethnicity. So, taking this into account, we wanted to see whether we can build group-specific models of public speaking anxiety. And the way we first did that is that in addition to the biobehavioral measures that we captured from the wearable devices, we also added in the input spaces the demographic and psychological trait characteristics of our participants. So we saw there that the combination, that these are the results when we only have the physiological measures alone. And by combining the physiological measures with the trait, anxiety, and personality characteristics, we can get an increase in our accuracy. Similarly, when we have acoustic and physiological measures and combine those with measures of language, ethnicity, and age, we also get a boost. And the reason for this might be especially because we didn't have only native English speakers, we had also non-native English speakers. So some of the acoustic measures were actually biased from the fact that many of our speakers were not native English speakers. As part of trying to perform a little bit more elaborate group-specific machine learning models, we then attempted to group participants in terms of their psychological traits. So here you can see an example where participants were grouped into 4 groups in terms of their extraversion scale and trait anxiety scale. And then based on these models, we tried to build different machine learning models for each group of participants. And then we evaluated our machine learning models compared to general machine learning models that were trained for all participants simultaneously. And we saw significant differences between the two. So our group-specific machine learning models were able to better estimate public speaking anxiety compared to our baseline general machine learning model. Now going to our third research question of whether systematic exposure to public speaking encounters can alleviate public speaking anxiety. We observed pre and post differences in terms of the self-reported indices, which means that after finishing up the virtual reality training, people reported reduced anxiety in terms of public speaking. And we also observed similar differences in terms of our physiological indices, which means that people produced less sweat and had a decreased heart activity between the pre and the post session. So we also observed similar trends in terms of a 5-month follow-up, which indicates that some of these benefits from the virtual reality training could actually translate in a more long-term, can actually have a more long-term effect. So to conclude, what this first part of our study has here is that we are trying to quantify public speaking anxiety unobtrusively through the biobehavioral measures that we are collecting from the wearable devices. We are also mindful of the large inter-individual variability that we have among our participants, and we're trying to build group-specific models that take this inter-individual variability into account. And now, as part of our current work, we are integrating those machine learning models that can track public speaking anxiety in real time. And then we are designing these personalized feedback interfaces for training, in which we will be conducting experiments in detecting anxiety and then providing personalized feedback to the participants while they're performing the training. And here I have put a small video of our project, so feel free to check this out as well. As part of our current work, this also inspired us to try to see different communication disorders for more vulnerable populations. And now we are starting to monitor and collecting data about veterans and interviews with veteran participants, and we are trying to quantify potential anxiety as well as potential limitations that this specific population might have in terms of successfully interviewing for a civilian job. So this was the first part of the talk that mostly discussed how we can leverage data that we get inside the lab to provide types of personalized training more in relation with the communication functions. Now, as part of our second part of the talk, we're going to discuss how we can leverage the findings that we get inside the lab in order to track a real-life behavior outside the lab in the real world. So as part of this, we have partnered with USC, in which they had a project on tracking stress and tracking mental and emotional outcomes for nurses. The motivation behind this is that nurses work in a very demanding job in a high-paced environment, and many of nurses during the long years that they might have been working, they might have adverse health outcomes. So the premise of wearable devices would be to be able to track emotion and stress in real time, and to be able to provide interventions on stress-related symptoms and cognitive decline in these people. Our data comes from 213 participants during a 10-week data collection, in which you use various types of devices to monitor physiological signals, and these devices include the Fitbit device, as well as this chest-worn sensor that you see here that collects the electrocardiogram signal. We also used microphone devices in order to collect speech signals, but due to privacy, we were not able to monitor the entire speech signal, so we had to extract measures on the signals while recording and only store those measures. We also had several ground truth assessments that were performed, that were taken once every day. These ground truth assessments were related to daily stress levels, daily emotions such as positive and negative affect, as well as in-role behavior and individual task proficiency. And these measurements were administered as a very brief survey through the mobile phone. The vocal and acoustic features that were extracted from this include jitter, shimmer, fundamental frequency, as well as the MEL frequency capsular coefficients, which are a compressed version of the Fourier decomposition of the original speech signal. We also extracted daily activity features such as the number of steps, sleep efficiency. These were measures that we were able to get from Fitbit, as well as physiological features such as breathing rate and heart rate variability. So in this case study, with the data that we got, what we attempted to do is that we attempted to see how much variability we get across our population in terms of the biobehavioral signals that we have. And in this left graph here, you can see for a specific signal which monitors the calorie intakes within a day, and each curve here is one individual. So you can see that there is a vast variability in terms of the caloric expenditure of individuals within a day. So we wanted to see whether there is a way to actually model this inter-individual variability in machine learning models. And the way we did that was that we know that conventional machine learning models mostly tend to model the distribution of each class. So if we have if we want to detect high stress versus low stress, we have data that we get from the high stress condition, and we try to fit one distribution there. And we also have data from the low stress condition, in which we are trying to fit another distribution. But the problem with this is that usually when we are modeling behavioral outcomes, data from extreme conditions might not always be available. And also the other thing is that one person's low stress condition might reflect another person's high stress condition. So we thought that an appropriate way in order to model this interindividual variability is to take into account distance learning or metric learning techniques that model pairwise similarity characteristics between samples of interest. The way we did this was through a Siamese neural network, which is nothing but it compares samples or pairs of samples in its input. We made sure to add pairs of samples in the input within an individual in order to measure differences, let's say, between low and high stress within an individual. And then it transforms those samples through nonlinear transformations in order to model their relative distance. And the way this neural network is trained is that these transformations should result in a low distance metric when these samples belong to the same class. And the same transformation should result in a higher distance metric when these two input samples belong to a different class. We also added an additional supervision layer here, and the way we did that was that this simple distance contrastive loss was able to model distances, but it doesn't really provide a class outcome. So that's why we added this additional supervision here, that it is trained in order to minimize the cross entropy loss, in order to provide the final outcome for the outcome of interest. And the outcome of interest would be affect, stress, and other types of behaviors. So we saw our results, and we evaluated our results in terms of correlation between the actual and estimated values of our behavioral outcomes. We monitored 4 different behavioral outcomes here, which correspond to the type of activity, the level of stress, the level of positive affect, and the level of negative affect. The proposed metric learning approach, distance learning approach, is depicted here with the yellow graph, and the general model that performs a simple linear regression is depicted with the blue graph, and the feed-forward neural network that essentially does not really leverage this distance-based modeling is being depicted with the orange graph. So we see that for most cases, our distance learning approach is able to provide some reliable estimates of the outcomes of interest. You can also see here that the correlations that we get, especially from this data set, are particularly low. So the reason of that was that the data that we got was data from 90 days. They were extremely noisy data, and the main challenge with this data is that people completed one self-report usually towards the end of the day or the end of their shift. So at the end of their shift, essentially they had to remember how stressed they are, the amount of positive affect, the amount of negative affect, and the way these outcomes can be triggered, these outcomes, for example, high levels of stress might be triggered 5 hours before this self-report is completed. And this kind of time lag between the actual self-report and when the actual behavioral outcome is manifested on the biobehavioral signals is actually a big limitation. And we're now trying to develop better ways in order to model this. We are thinking of developing attention, to take into account attention-based models and other types of models that might be able to better quantify this discrepancy. So I added this slide after I had some discussions in the morning with Irina and some other colleagues from the Department of Statistics. We attempted to use similar distance-based models in order to represent glycemic responses of individuals with diabetes. So an important thing about individuals with diabetes is their diet monitoring, and what they eat is actually depicted in their continuous glucose monitoring signals. So this is how a signal would look like if there is a high carbohydrate intake, and this is how a signal would look like if there is a high fat intake. So we attempted very similar distance-based methods in a personalized manner in order to see whether these methods would actually achieve a better meal estimation compared to general methods that really do not involve this distance-based learning. And we found some promising results there, and we're now in the process of exploring our results more. So to conclude, this second thread of our presentation attempted to see whether it is feasible to track human outcomes in real life from multimodal data, and whether basically it would be effective to fuse multimodal data from accurate tracking, and most importantly, whether personalized models that take into account distance learning approaches and metric learning approaches could provide reliable estimates to behavioral outcomes. And our premise there was that these models might be able to provide even more reliable estimates of behavioral outcomes compared to general-based models. So as part of our future work, we will attempt to perform a longitudinal monitoring of biobehavioral patterns and try to match exactly basically when a stimulus happened and when the biobehavioral response might have happened. And we're also going to try to detect abnormal events that are happening throughout the day. And now we wanted to transition to the third part of the talk, in which we wanted to see whether there might be specific privacy concerns that we can take into account when designing our machine learning models. So recently, there have been a lot of privacy concerns from the users, especially when collecting audiovisual data in real life. Many people have Alexa devices in their home or Google Home devices, and of course we know that these devices store our speech data, so there have been, of course, a lot of privacy concerns on where the data is stored, where the data is processed. And now, similarly, if we extend this to the medical field, surveys have shown that only 37% of patients feel comfortable in sharing their data, while the rest of their patients do not feel comfortable at all, or really want to know what is the purpose of this data being used. And of course, there are several privacy violations from health administrations that really sometimes might impose additional risks in users' privacy. So we wanted to see that these privacy concerns and examining these privacy concerns more in terms of designing machine learning models that eliminate user-dependent information but preserve emotional information. So of course there has been a lot of work in that front. First of all, in terms of consent management, where researchers have attempted to use user-friendly consent in order for users to understand exactly the types of data that are being recorded. There has been work in terms of multi-stage user authentication, and recently there has been prior work in terms of differential privacy approaches that attempt to inject a controlled noise to prevent user identification. These approaches have been particularly studied for biomedical data such as electronic health records and genomic sequences. So with the advent of neural networks, of course, there is a great promise in modeling behavioral outcomes with the large data and neural network models, but we know that neural networks can be generalizable to different tasks. So when a network is being learned on a specific task, let's say on the task of emotion recognition, it might be also used for user identification, because the neurons and the parameters of the network might have actually stored information that is generalizable beyond the primary task of emotion recognition or behavior recognition. So in that front, we wanted to answer two main research questions. The first research question was whether we can quantify user identification risk when we model behavioral outcomes through conventional neural networks. And the second research question was whether we can learn anonymized signal transformations that preserve emotional information but do not preserve user-dependent information. And this is a case study where we designed anonymized models of facial emotion recognition, which also comes with several challenges. So prior studies that have used, that have attempted to anonymize machine learning models have mostly worked on general activity recognition, where they had videos that were capturing people's activity from long distance to the actual faces. So you can understand that by capturing the faces over a longer distance in a frame where multiple people are around, of course the resolution of the face is lower, therefore the amount of the risk of user identification is likely to become lower as well. And also there was an additional challenge in terms of the high interdependence between user identity and emotion information when we train our neural network. So the contributions of this work is that we try to explore user identification risk specifically in the context of behavioral outcomes and emotion recognition. And then second, we proposed an iterative adversarial learning with alternate training between minimizing the emotion classification loss and maximizing the user classification loss. We employed, in order to validate our data, we employed 3 data sets that include, the first 2 are the Japanese female facial expression data set and the Yale face data set. All these are publicly available. And these include faces that are captured in close proximity to a user. And most of these include active faces with using only a small number of samples. The third data set that we used also includes both acted as well as spontaneous emotional expressions and also has more images available. So coming back to our first research question on whether we can characterize and quantify user identification risk, the way we approach this problem is that we used a machine learning model that is very commonly used for facial-based emotion recognition, and that is a convolutional neural network. We first trained a convolutional neural network, as you see here on the left side of the screen, for the task of emotion recognition, and then we wanted to see how much user-dependent information is embedded in these inner layers of the network, in these convolutional layers of the network. And the way we did that is that we fine-tuned these last fully connected layers of the network for the task of user identification. So we understand that if we are successful in the task of user identification based on this fine-tuned convolutional neural network, then this means that our emotion model actually preserves user-dependent information. And that was actually the case. Here we can see the results of our emotion classification using a convolutional neural network solely trained on emotion classification. Here we can see our results on face user identification using, again, a convolutional neural network solely trained for user identification. And then finally, in the last column, we see the results that we get from this fine-tuned neural network, which is first trained on the result of emotion recognition, but then fine-tuned on the result of user identification. So we can see that the accuracies, the user identification accuracies in this emotion-to-face model still end up being pretty high, which means that the emotion recognition model actually preserves user-dependent information in its convolutional networks. And the same thing happens when we actually blur the image. So we see that even if we blur the image, we still have a significant amount of user-dependent information preserved in these emotion classification models. So going now to our second research question in that front of how we can learn anonymized signal transformations that preserve behavioral information. The way we tried to do this is that we wanted to have this convolutional neural network and this convolutional learner, these convolutional kernels, to preserve as much emotion-dependent information as possible, but eliminate as much user identification information as possible. So we trained a multitask neural network in an adversarial approach. We superimposed in this initial convolutional layer a part of fully connected layers that performs the user identification task, and then a part of another set of fully connected layers that performs an emotion identification task. And the adversarial learning trained this entire network in terms of minimizing the emotion recognition loss, but maximizing the face recognition loss. So what we did in terms of iterative learning, because the convergence of this adversarial framework was very difficult to achieve, especially because the tasks of emotion recognition and user identification from closed captioning facial expression are very interconnected. What we tried to do is that we proposed this iterative adversarial approach, in which first we trained a good user identification model, and then conditioned on this user identification model, we trained our emotion recognition model in actually minimizing the user identification loss. So we see here the validation losses that we get from this proposed approach. We can see that this is the validation loss for emotion recognition that stays pretty much low. And then this is the validation loss for user recognition, which in the beginning is low, but then it's pretty high, which is essentially what we want, meaning that our convolutional kernel our convolutional kernel starts to forget user-dependent information. And these are the results that we got in terms of emotion classification and user classification with the proposed approach that has this adversarial learning with iterative weight training, as well as the baseline approach that uses this adversarial learning without alternate weight training. So we can see that with the proposed approach with the orange line, we still achieve some decent emotion classification accuracy, but the user classification accuracy is pretty low, which was our goal. While with the baseline anonymization approach, we were not able to always achieve such a low degree of user classification accuracy. And these are a couple of examples that which are the results of our convolutional output from our convolutional kernels. We see here in the first row are our original images. The second row presents the transformations from the convolutional kernel that result from the emotion classification model. And we see that this emotion classification model retains significant amount of facial information, including the face contour, which might be a potential reason why we have a high degree of user identification in our network. Now, the last row here is the proposed anonymization approach, and we see that for the proposed anonymization approach, only parts of the mouth region and the eye region have been retained, which are really, these parts are really indicative of the emotional information, and we do not see any face contour or any other significant information that has been retained from this approach. So this might be a nice intuition of the reason why the proposed approach might work better compared to previous approaches. So to conclude, in this thread of our work, we investigated whether conventional emotion recognition models actually retain a large degree of user information, therefore have a high user identification risk. And we also attempted to design a machine learning algorithm that eliminates this user identification risk while preserving behavioral information. As a future part of our work, we are attempting now to learn anonymized images as well as speech signals that preserve utility information but do not preserve user information. And we're also looking at personalized anonymization and how essentially different people might perceive privacy risks for these different models. So to conclude, what we presented today was a research framework in which our focus is to model human behavior through the various multimodal biobehavioral indices that we get from wearable devices and Internet of Things devices. We demonstrated 3 research threads in which first we attempted to provide to inform personalized training applications through biobehavioral information. In the second research thread, our goal is to track real-life human behavior through wearable and IoT devices and using machine learning models and personalized models. And then in our third research thread, our goal is to learn anonymized biobehaviorally aware machine learning models that preserve utility outcomes but do not preserve person-dependent outcomes. So As part of our work, we have been also working in several other research threads. For example, we have been working on providing generalizable models of emotion recognition. So we know that labeling human behavior can be actually very expensive, because labeling sometimes either requires human feedback from the user or requires feedback from an expert annotator. So our goal with these models is to see how we can develop few-shot learning approaches that take into account publicly available data of affect or behavior, and also have a few labeled samples from the in-domain experiments that we might be interested in modeling. As part of our work, we are also collaborating with colleagues from the Department of Construction Science, in which, and specifically Dr. Ryan Nunn, in which we are trying to develop a map of an affective digital twin city. And in this part, we are leveraging wearable devices, and then we are modeling affect with respect to different parts of the urban environment. And finally, in the last couple of months, we also focused on trying to learn to perform sentiment analysis from YouTube videos, especially for the case of COVID-19, and to see how different people might perceive the different stages of the COVID-19 pandemic. So in that, I would like to thank you, and of course thank my students in the lab, who are actually the people who do most of the work. So thank you so much.
Okay, thank you. That's a wonderful talk, and it's time for questions. Do we have any questions for Dr. Chaspari? You can either just turn on your mic, or yeah, go ahead.
Sorry. Very nice talk. I'm sorry I had to be a little late on the beginning, but I'm gonna ask very selfish questions. I was wondering if you can go to your glucose slide.
Yeah, of course. I just added it after our talk, so I'm sorry if that was a little bit messy.
No, this is great. So I'm really curious. So when you input those profiles, so I understand that you have to pick the time frame to make sure that they're all for the same time. But when you enter it so that you can get a CMI's loss, it does not preserve the time information, right? You just throw it in as a vector feature.
No, we didn't throw it in. No. So in this case, we just extracted the features. Basically, we extracted the area under the curve across different parts of the curve. And we threw in these features in the CMIs, not the actual.
Okay. So you didn't use the actual curves, actually?
No. Okay. And actually, because the data is so low, if you use the actual curves, it's not going to work, I think.
With the neural net, I don't think so.
Yeah.
No, but okay, great, thank you.
Yeah.
Any other question for the speaker?
So I just had a question with the identification of the individuals who you were collecting emotional measures from with the photographs.
Oh, here.
Right.
Yeah.
How much easier does this problem become when you get more and more individuals? It seems if you have a limited number of people participating, the identifiability issues are more severe than if you have a large number of participants, right?
Yeah, I agree. So I think in all cases we had a smaller number of participants. So I should have actually added the number of participants here, but I think we were talking mostly about 20-30 participants. Yeah, you're absolutely right that this might not always be an issue if we have, let's say, 100 or 200 participants. But mainly that was, in our community, and in many communities, like sometimes people collect data from 50 participants and then they distribute the speech data or the images without, of course, distributing identifiable information. But the moment you put this signal there, you immediately have the identifiable information. So this is what kind of inspired this approach, that even like it's very custom. Sometimes we can share data sets with fewer participants, and then the re-identification risk might be pretty high. But I completely agree. The more participants you have, probably these risks might be lower.
Any other questions?
Can I ask one more question?
Yes, you can.
Thank you. So you talked a lot, I think in the second project, about how you have this data from many different devices. So you have Fitbit data, and then, you have multi-model data layers. And because you have this multi-model data layers coming from the same participants, you would expect that there's some sharing of structure that happens across the layers for the same person. So I was just wondering if when you build these models using the features from this data, have you tried to take into account that those features are sort of grouped naturally based on the modality that they're coming from, or they were just kind of put in as they were?
That's a great idea. We haven't done that. And that's a wonderful idea because, for example, heart rate features are usually very much associated with activity features, right? Or heart rate variability features. So I think that's a great idea. And also these features might have their own structure by themselves. We have definitely tried to eliminate features that are very much interdependent so that we do not really have dependencies between really highly correlated features on our models. But that's a great idea. And I would love to discuss more.
Thank you.
Yeah, thank you so much, Rina.
Is there any other questions?
I have a question. I noticed that on your Vita that you do a lot of signal processing, and I'm wondering how you use signal processing in all of these studies.
Yeah, so as part of my PhD, because I was from a signal processing lab, we have been doing sparse representations. So, for example, we have been trying to develop knowledge-driven dictionaries for specific types of signals. For example, we know that the electrodermal activity signal or the continuous glucose monitoring signal, in this case, have this very specific structure where the signal goes up and then goes down, and the electrodermal activity signal actually it goes up and then it has a slower decay. So we have tried to do these parametric signal representations with parametric dictionaries, and we have designed a dictionary learning framework that learns these parameters from the data, and then it uses these dictionaries in order to extract meaningful features from the signals. In the last 3 years, it's true that there are more machine learning applications coming up. So in our lab, we have transitioned a little bit more into the machine learning applications, and but we are trying to be very mindful in the feature extraction part, and at least try to monitor our data and perform all the appropriate denoising methodologies and data curation methodologies. But I also think that it's a very good way moving forward would be to design machine learning models that are mindful of the structure of the signal. Because if you think about it, this is what convolutional neural networks do for images, but that's not always the case for all the biomedical signals that we are dealing with.
Right, and of course, traditional models are difficult with such data, right?
Yeah, yes, I agree.
That's where wavelets and things like that come from.
Exactly.
Okay, thank you.
Thank you so much.
If I can dovetail to the previous question, sometimes the shape is not informative or not discriminatory, and your data or your measurements look like pure noise. And I wondered, are you using some of these long memory measures or fractality, multifractality?
Sorry.
Yeah.
So we are definitely trying to take into account time dependencies from the problem with the long memory measures. If you're referring to the long long-term memory neural networks is that they require a lot of data. So that's why we barely use them, because we do not have really that amount of labeled data, at least. But we're definitely mindful of the time dependence in the signal, which is something that we are trying to integrate when we're doing our feature extraction. So at least we're trying to integrate that with appropriate time-dependent models, even just some simple, let's say, linear oscillator models that can integrate some of this time dependence in the signal, and things like that. The multifractality is something that is very interesting. I haven't worked with such types of measures, but I think it's very interesting to integrate those measures in the signals, for sure. Yeah.
Okay, are there any other questions? Any more questions for the speaker?
Can I ask a question?
Yeah.
Can you hear
Go
me?
ahead.
First, thank you
Yes.
for the great talk. I have a small question. So I'm interested in the loss function. So there you use the emotional point minus the individual point, and there is an alpha. Do you treat it as a model, like alpha in the model, or do you treat it as a hyperparameter?
We treat it as a hyperparameter.
Oh, okay.
Yeah.
Okay.
But I could see the value of treating it as an additional modeling variable. Yeah.
Okay.
Yeah.
I see. Thank you.
Yeah, thank you so much.
Any more questions for the speaker? Okay, if there's no more questions, I would like to thank Dr. Chaspari for the wonderful talk, and thank you very much.
Thank you so much. Thank you, everyone.
Yeah, thank you.
Have a great day.
Bye.
Bye-bye.
Thank you. Have a good weekend. Yeah, bye.
Thank you.